Good morning, everyone. In today's mini lecture, we are going to talk about the electron configuration. As I posted earlier, I was very proud of everybody. Y'all have done an amazing job going through and figuring this out, but I wanted to go back in and just help explain it so that there's no more misconceptions. So first of all, the electron configuration deals with what we've been going over, which is our energy levels and different orbitals. First of all, if we look at the energy levels, we'll see that the periodic table has 7 periods. Each one of those periods is an indication of another energy level. Now, each one of the energy levels can contain a certain number of suborbitals. Those orbitals are called the S, the P, the D, and the F orbitals. So if I look at the S orbital can hold 2 electrons. So therefore, if you were going to draw out an orbital diagram, the S would have one box, and that one box could hold an electron that would go up, and then also an electron that goes down. So this is how it looks as far as an orbital diagram. Now, if I look at the p orbital, the p holds 6 electrons. So each one of these little orbital boxes can hold 2. So they're connected together because I need a total of 6. So as the electrons fill them up, it'll go 1, 2, 3. Did you notice how there was 1 electron per box? Now they start to double up. 4, 5, 6. If I do the d orbital, it will hold 10 electrons, and the f orbital would hold 14 electrons. So if I drew out my d orbital, if I had 10 electrons, that means I would have to have 5 orbital boxes. If I drew out the f orbital, since it has 14 electrons, it would have to have 7 orbital boxes, and that would give us a total of 10 or 14. All right, so when I look back over here at the periodic table, you'll see that the periodic table is laid out into 4 sections. This section right here, which is the alkali earth metals, are going to be the s orbital. S holds 2, that's 1 and 2. If I look at the p orbital, this block over here is called the p block. And what you see is you have 1, 2, 3, 4, 5, 6. The d block is in here, and that is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And that represents each one of the electrons that it can hold. The F block is down here. We're not going to deal with it just simply because most of them are rare metals or rare earth metals, or they're radioactive. So now what I want to do is draw for you the electron configuration pattern. So we already said that you have 7 periods. So I'm going to go 1, 2, 3, 4, 5, 6, 7. So the pattern is the s orbital is the least, so everybody gets a s orbital. Then you come over 1 and down 1, and then you get a p orbital. Over 1 and down 1, a d orbital. Over 1 and down 1, and then final f orbital. Now this is called the diagonal method, and the way that I do it is I just say 1, 1, 2, 2, 3, 3, 4. So I'm going to always start up here, and I'm going to go in a diagonal back this way. 1, 1. Now, the reason I'm saying 1, do you see how I went through one letter? Just the S and the S. Now it's going to go 2, 2. That's because I went through an S and a P. Now, if you notice, I'm always starting up at the top, and then I'm going back down to my left. Then it goes 3, 3, 4, and then that final F right there. So up here we have start. So I can go through and start writing out my pattern. The first letter I went through was an S, and it was on the first line. The second one is a 2S. The third one, if you notice, I'm coming back up here. I go through it, I'm coming back up here. Now is a P on the second line, so I put 2P, then 3S. I come back up. This is why it's called a diagonal. I go 3P and 4S. I come back up and it goes 3D. I'm just going to keep right on going. It goes 4P, 5S. And if you notice, I'm just right here, back up to here, and it's 4D, 4D, 5P, 6S, back up to the top, almost finished, 4F, 5D, 6P, 7S, and finally back up here to 5F. Now, we said that each one of those are going to contain either an S2, a P6, or a D10, or an F14. If I went through and counted all of these up, all the electrons up, it would cover all the elements on the periodic table. So if you see these little numbers like this, 2, 2, 6, that isn't an exponential number. What that means is you have one S, and in that S you have 2 electrons. 2S, 2 electrons. 2P, 6 electrons. So if I wrote that out right there, that would be 1, 2, 3, 4, and then 6 more would be 10. So that would be neon right there, the electron configuration. So this is the pattern. It represents the periods and the sections on the periodic table. Now what I want to do is make sure that we can write out the electron configuration and the orbital diagrams for different elements. So if I look at this, I have 6 electrons. The electron configuration means that I would start with 1s. I'm sorry, I used a cursive S. 1s, and there would be 2 electrons. 2s, 2 electrons. So far I've put 2 here, I've put 2 here, that's 4, but if you look I have 6, so I'm not quite through yet. So I'm going to say 2p. Now even though the p will hold 6, I'm not going to fill it up. All I need is to have 2 more electrons in it, because now I've got 2, 4, 6 electrons. But before I can go to the next energy level or the next orbital, I do have to fill the one up before it. So this is the electron configuration. Now I'm going to do the orbital diagram. So now I'm going to draw a box, and that box equals the 1s. There are 2 electrons in that 1s. The next box is going to be just slightly higher, and I noticed that a lot of you, when you did this, you just kept them all on the same level, which is perfectly all right. I just do this so that you can see that it contains a little bit more energy. And again, it's going to be full, and then finally we do the 2p. And remember, p is going to have 3 boxes into that p orbital. So we only need 2 electrons. So we don't fill them up. We're going to put 1 in each box. So this is going to be the electron configuration and the orbital diagram for, and that's carbon. So the next one that I want to do is, just to give you one that's a little bit bigger, is potassium. Potassium is going to have 19 electrons. So I'm going to say 1s2, 2s2, 2p6. Now, somebody's going to say, well, how did you know that? Well, I went back to my original configuration, and I'm just filling them up. This is what I always use. So I'm going to come back over, and I'm going to say, okay, I've got 10. I still need 9 more. So after the 2p is going to be 3s2, 3p6. So that's a total of 18, and then 4s1. So that's going to be my electron configuration for potassium. And if you notice, they have 1 valence electron. So I'm going to come back and draw it out. So it looks almost the same as the other one starting out. I got 1s. I'm going to come up just a little bit for the 2s. And again, 2p, one at a time. Then they double up. That's 2p. And then, oops, 3s has 2. And then 3p. And if I look at this so far, it's 2, 4, 10, 12, 18. So I'm not quite finished to my 19. So I need to come back over here and look and put 4s, and there is 1 electron. All right, so let me show you how let me show you how all of this ties together with the periodic table. So we said that this is our S group. This is the sublevel. We have the potassium that has and it ends in 4s1. Well, whenever we numbered 1, 2, 3, 4, 5, 6, 7, that tells us the periods. 1, 2, 3, 4. So it's 4. S shows you the location. It's going to be either this one or this one. And since it's only 1 over, I go 4s1. Hey, potassium. We go back over and we look at the one we did for carbon. Carbon had it ended with 2p2. So again, 1, 2, but this time we're in the p block. And there's only 2 of them, so I go over 2. 1, 2, and there's carbon. Is that not cool? Let me show you, just to make sure it works with all of them. I'm going to pick strontium here. So the first thing I do is count 1, 2, 3, 4, 5. So it's going to end with 5, or the 5 energy levels, and then it's over here. That means it's still in the S group, but it's S1, S2. 5s2 would be the final electron configuration for strontium. If I turned over to sulfur, sulfur is here. It is in the 3rd period. 1, 2, 3. It's in the P group. 1, 2, 3, 4. 3p4 for sulfur. So guys, I hope that kind of helped explain a little bit about how the electron configuration is a little bit more accurate than Bohr's diagram. It allows us to look at any of the elements on the periodic table and to determine their valence electrons and then, of course, the oxidation numbers. All right, hopefully that helped a little bit. Thank you.